In earlier modules, you learned to calculate the area under simple curves and the area of the region enclosed between a curve and a line. In this module, let's see the procedure to find the area of the region enclosed between two curves. Consider two curves, f of x and g of x. Let's find the area of the region enclosed between these curves. First, divide the shaded region into thin vertical strips, each of width dx, and then perform integration over the entire region. But the question is, what is the span of this entire region? To address this, we have to observe the points of intersection of the curves. These points are the end points on both sides of the region, which can be found by solving the equations of curves. Let these points be x1, y1 and x2, y2. The area of the region can be found by using the formula integral of y dx from x1 to x2. Here y is the height of the strip, which is equal to f of x minus g of x. Here, we are subtracting g of x from f of x, because the value of the function f of x at any given point is greater than the value of the function g of x. If the graph is not available, then we mathematically check whether f of x is greater than g of x. If f of x is greater than or equal to g of x, then y is equal to f of x minus g of x. On the other hand, if f of x is less than or equal to g of x, then y is equal to g of x minus f of x. The intuition here is that height is always a positive quantity. Thus, the integral to calculate the area of the region is as shown. Using this formula, we can estimate the area of the region enclosed. Let's now see the interpretation of this integral. The integral can be written as shown. Graphically, it means that we first calculate the area under the curve f of x and then the area under the curve g of x. After that, we subtract the area under g of x from the area under f of x. Now, let's take another case. Consider the graphs of the functions f of x and g of x shown here. Let's find the formula to calculate the area of the region enclosed between these two curves. In the interval a to b, f of x is greater than or equal to g of x, and in the interval b to c, g of x is greater than or equal to f of x. So we divide the region into two parts and write the integral as shown. To understand the discussion so far, let's consider an example. Suppose we have the curves f of x represented by y square is equal to 8x and g of x represented by x square is equal to 8y. Let's find the area enclosed between them. Solve equation 1 and 2 to get the points of intersection of the curves. This will help us to identify the limits while performing the integration. On solving, we get x is equal to 0 or x is equal to 8. Substituting in either f of x or g of x, we get the points of intersection as 0, 0 and 8, 8. Also from the graph, it is visible that f of x is greater than or equal to g of x between x is equal to 0 and x is equal to 8. This can also be achieved mathematically. First, express both the equations in terms of y. Now, substitute different values of x between 0 and 8 in the equations of the graphs. Observe that the value of f of x is greater than or equal to the value of g of x at all the points. Now, if we take a strip of width dx and height y, where y is equal to f of x minus g of x, then the area of the region enclosed is given by integral of root 8x minus x squared upon 8 from 0 to 8. Simplifying this integral as shown, we get an expression between the limits 0 to 8. Simplifying this further, we get 64 upon 3. Hence the area of the required region is 64 upon 3 square units.